new approach to the idea of gravity, that it's not a fundamental force, but it's an emergent phenomena. Tonight, Dr. Berlin will explore the core ideas behind his research and examine the implications of this fast-emerging revolution of our understanding of the universe. Ladies and gentlemen, please join me in welcoming Dr. Berlin to the stage.
Thank you very much. Thank you. Thank you very much. Yeah, it's a pleasure to be here and to be telling you this evening about what I think are exciting developments in theoretical physics. In our understanding of gravity, we are making progress, and we're moving towards, again, a new theory, a new view on gravity that differs from the old theory in the sense that it transcends it. It sort of contains it, but takes the next step. And that's also because there are indeed important questions to be asked or answered about gravity, which have to do with our universe. In particular, there are questions related to dark matter and dark energy, which together I call the dark side of the cosmos. I will be explaining that during the lecture. It's also a timely lecture because yesterday the Nobel Prize in Physics was awarded for 3 researchers working on gravity and who together did very important work in making it possible to detect for the first time gravitational waves. And also that I'll explain later more precisely what was being done in this experiment, but this was a confirmation of the theory of Einstein. So Einstein already 100 years ago predicted the existence of gravitational waves. So now the theory is confirmed. You might ask, well, why do we need a new theory? And this has to do with theoretical advances, because theory always develops further. It has to do with observations, things we don't understand about gravity, and I'll explain that. But also there's a bit of a philosophical point of view, and I'm going to start with that one. Because the way that science progresses has very much to do with the times that we live in, and also with the technology that we use. And normally we would say that science helps us to develop technology, but there's also the other way, that our current technology influences the way we think about science. So we go back to the Middle Ages or a little later, we have cannons and think about ballistic motion like cannonballs, and these are objects where we don't even ask the question what they're made of, they just move. And this is how Newton sort of started. Of course, in the 19th century, people made steam engines, and this is where we talk about gases that have pressure and temperature. Even then, people didn't think so much about what it's really made of, but slowly one started developing the atom picture. But the revolutions that happened in the 19th century were very much related to this existence of the steam engine. The previous century, we developed things like televisions and other things. And a television, if you think about what that is, it's actually a particle accelerator, because it accelerates electrons which are moved around with electric fields and are projected on a screen, and then we see photons coming out. So the ideas of forces and particles is really the language of the 20th century. And there our understanding of nature was in terms of the most fundamental building blocks, which are elementary particles, and the fundamental forces. So we built theoretical physics using that language. Today, we are already far in the 21st century, and again, we are having a different type of technology. We're having smartphones, we have computers, big data, and most of what we're doing every day has to do with somehow with information. And that's again a new language. And this is again also influencing the way we think about science. So I'm going to tell you that today is that the new view on gravity has to do with information. And because it's basically the language that we're developing in our current century. So we live in an information age, but what is information? You might say, well, it's what I read in a newspaper because I'm interested in certain things. But there's also an abstract way to think about information as the way it's stored in terms of bits. And then we don't even look at what is really written somewhere, we just count, for instance, how many bits we have, how many bytes. And so I will think about information in this more abstract way. So we're going to even talk about information that we cannot really access, but we still have a way of counting it by saying how many bits are used. There's also another development going on, namely we're going to make things smaller and smaller, and then we're going to look at even subatomic scales or atomic scales where things become quantum mechanical. And then information even has another meaning, because in quantum mechanics you get something called qubits, so not bits like zeros and ones, but there's things that are somewhere in between. So this is Mike Lazaridis, who's indeed already one of the people who invested heavily in the idea of developing quantum computers, and I think here he stands in front of something that has many qubits in it. And qubits are funny objects because they can do things that are only possible in quantum mechanics. They can namely not just be 0 and 1, but they can be something in the middle. And furthermore, they can do something called being entangled, in the sense that one qubit here is doing the same thing as somewhere else. And this is, say, 2 qubits that are entangled, where the 0 is on one, is combined with the 0 on the other, or the 1 on the other is also combined with the 1. This is an example of entanglement. So this language we're going to use even in our universe. So we're going to think about the universe in terms of information and also in terms of this entangled quantum information. So my new view on gravity has to do with a new view on the universe built out of information, and we're going to try and understand what then the forces, in particular gravity, then comes from this new language. So this is immediately related to another concept, again, sort of a little bit of a philosophical one. Namely, we used to think in the 20th century that everything can be reduced to the tiniest building blocks. Like we have elementary particles. If we know what elementary particles do and their forces, we can derive everything else. This is a reductionist point of view on nature. We're living in an age where things are changing, where we start realizing that when we build things that are larger, and much more, many things are involved, that maybe this reductionist point of view doesn't give all the answers. So let me ask you, what is this? You probably don't recognize it. It's just a set of pixels. But to show what it is, let me just zoom out a bit. But it's the same set of pixels, but a little smaller. And now it's a picture where we suddenly see what it is. Of course, these are mountains, there's a lake and trees and so on. No, it's a collection of pixels. And here we have suddenly giving meaning to a collection of objects where microscopically it doesn't exist. And this is the same in nature. If we ask what things are made of, then some of the terms that we use, like maybe even matter or space and time, may not exist. And this is sort of where we are going to. And there's, of course, examples in nature that are more down to earth. Actually, I already mentioned this, but let me tell you then what the term is. It's called emergence. Namely, we use concepts and observe phenomena at macroscopic scales, which are derived from the microscopic scale, but have a priori no meaning in that language. So the language that we use at macroscopic scales is different than the microscopic. And we do use concepts and things that are not meaningful, so we have to derive them. We have to define them in terms of what's underlying. So this is an example of emergence in physics. If we look at a room full of gas and molecules that are moving around, then we can describe it in terms of temperature. And temperature is a property of all of the gas molecules together, but an individual molecule doesn't have a temperature, because actually the temperature is defined as the average energy per molecule. So there we have to define quantities that we normally use, like pressure and temperature, precisely in thermodynamics, from a more statistical perspective on the microscopics. This is an example of emergence. And an important role in this is played, again, by what's called the entropy, which is namely, if I look at all the gas molecules in here, I don't want to know what they're exactly doing, but I can count how many possibilities there are. And that's the entropy that measures the number of possible states that these molecules can be in. And it actually tells you the amount of information that's needed to describe all those states. So here we already see a link with information and a quantity called entropy. That link has been made precise by Shannon. If I have bits, so these are coins, can be zeros and ones, but can be ups and I mean, all kinds of ways you can make choices. But here I have a coin which has 4, well, heads or tails. So there are 4 possibilities if I have 2 coins. So there are 4 possible states. So that's 2 to the n, if n would be the number of coins. And if you take the logarithm, and here I take the log 2 logarithm, then you count basically the number of these bits. So entropy can be thought of as counting how many bits can I assign to, do I need. And also entropy can usually be thought of as sort of a measure of chaos. That's how most people think about it. If there's a gas that does all kinds of funny things, and there's chaotic, then we have an entropy associated. This is a state where the yellows are on one side and the blue on the other side. Here they're mixed. Clearly this has more entropy than that, because there are more possibilities. Here also, if all the gas molecules are in part of this box, and here they can move around in more locations, I have more entropy here, also because there's more information needed to describe it. So the link between entropy and information is going to be important. So if I talk about information later on and you wonder what I really mean, it's counting the number of bits. I'm going to introduce this idea of qubits later also, because it's going to be also quantum mechanical points are important. And I'm going to end this talk of this lecture actually by explaining you what this has to do with a new view on gravity and also the dark aspects of the universe. And let me show you already a picture that I'm going to explain. It's almost like this picture actually came from the poster of my lecture. It's a galaxy according to Einstein's general relativity curve space-time, but I'm going to think about this in a different way, where there's information around it having to do with the dark energy in the universe. And I'm going to explain phenomena that we don't understand about galaxies based on this idea of gravity from information. Now I'm going to start over again. I gave you sort of a summary, an idea of where this lecture is going to. But now I'm going to start at the beginning and really start from gravity through the centuries and then get to the end again in this picture. So this was more a philosophical introduction, but now you at least know the concepts that I'm talking about. So I'm going to start again with Newton. So Newton told us how gravity works. Of course, Newton explained that the moon and the earth are rotating around each other by the same force that makes the apple fall. And he did this with a thought experiment. He had an insight. I told you already about cannons, and actually he did a thought experiment with a cannon. He thought about a cannon on top of a hill, which if you shoot the cannonball, it will fall down and hit the earth. But he imagines shooting it, giving more speed, more velocity, so that it starts falling and eventually it starts missing the earth. So while it's falling, it starts going around. So there's a trajectory, actually, it's not drawn here, which is sort of falling down on the earth. But if you hit it fast enough, you can actually make it go around and eventually come back here. It never goes further down because the energy is conserved, and so it comes back to the same point. If you shoot it harder, it becomes a circle, and if it then larger again, it's an ellipse. And then there's a trajectory where it never comes back. It's a parabola. And then you have things that are even further out, and then you escape away. And this idea that falling and going around the Earth was the same thing, that is how we got to the idea that basically the moon is falling continuously, but it's missing the Earth all the time. This is what it makes it move around. This thought experiment gave him eventually idea also where all these shapes of the trajectories came from, and this gives you also a force law, and this is Newton's famous law of gravity. So the law of gravity is, well, probably familiar. It tells you that the force is proportional to the size of the masses. I have a big mass, say, and a small one, either the Earth or the Moon, or the Sun and the Earth. Then you multiply the two masses, so it's proportional to the two masses, but it's inversely proportional to the distance between them. So it goes like 1 over r squared. And that's actually the same way that the size of a sphere grows. And actually, want to say, namely, if I go twice the distance, so this is one distance to the Earth, to the Sun. If I go twice the distance, actually, the force goes down by a factor of 4. And this is the same way that the area grows. So there's some way in which this goes like 1 over the area. And actually, this area plays an important role in what I'm going to say, because it's going to link to something that has to do with information. Of course, Newton's law has been tested very well, and this is also why people initially didn't doubt it to be right, because, I mean, you can test it by making its predictions, namely looking at the prediction. Here, the velocity is actually calculated using Newton's law, and you find that the velocity goes down as a function of the distance. So these are the planets, and you find that at larger distance the velocity is less. And this has been measured, and this is precisely what the measurement does. It follows the prediction of Newton. So this works very well. But then if you go to the planet that's closest to the sun, which is Mercury, there's a tiny deviation. So Newton would have predicted that the orbit of any planet has this ellipsoidal shape, and that these 2 points always are staying at the same location. This does not happen with Mercury. It actually rotates a little bit like that, and it rotates with a few degrees per century, actually less than a degree. But this has to be explained either by changing the law of gravity or by postulating some additional mass. And this is sort of what people did. People thought there might be some additional dark matter or some planet closer to the sun that would explain this. And they searched for it for half a century. They didn't find it. Of course, we now know that this is an indication that there's something wrong with Newton's theory. Not really wrong, at least it can be improved. And this is what Einstein did. He explained this phenomena by changing the gravitational law, not by dark matter, but having a different view on gravity. So his view on gravity, and that's a century ago, was that gravity is a consequence of how space and time are curved. This came out of his theory of relativity, where he introduced, well, motion comparable to the speed of light, or he at least made sure that the relativity postulates are consistent with the way that we think about gravity. For instance, that a signal cannot travel faster than light. And then the only way that can be done is if you think about space itself as sort of a dynamical object that can curve, and mass then influences the geometry of space-time and curves it in such a way that objects no longer move in straight line, but start going in elliptical orbits, at least approximately, because this, if you do this for Mercury, it would actually explain exactly what Mercury is doing, and he calculated this, and it confirmed. Actually, his theory got confirmed even very quickly afterwards for another prediction, namely, he also predicted that gravity would bend light. So if space is curved, then light is also affected by gravity, and if there's a star here, then the light would travel, if there's a mass between us, not in a straight line, but in a curved line like that. And that has a consequence, because then if we look at it, we don't see the star at its location, we see it actually slightly shifted, because we always think that light goes straight, and so we see the image there. So light gets bended a bit, and this is a consequence of Einstein's formulation of gravity, and it got confirmed by looking at a solar eclipse already like a century ago. The other prediction, and indeed what I said, was the lensing effect. Is related to it, because this is where you think about a source here behind the object. You see light going towards the Earth, but it can go in 2 ways, or even in many ways, because it can go up or down. And then you see the light from something behind, and actually it makes a ring, because it can curve around in all directions. And this is called the Einstein ring. It's a beautiful confirmation again of the way that gravity works according to Einstein. Now let me now come to the confirmation that I introduced at the beginning, namely his prediction of gravitational waves. So we're going to talk about black holes later, but gravitational waves are waves in the shape of space-time itself. Actually, it's ripples in space and time itself that propagate with the speed of light. I already told you that gravity cannot be transmitted instantaneously, because then it would go faster than light. So if something happens to gravity, it has to travel out and travel towards us. And one of the most spectacular events that can happen is if two black holes, they are rotating around each other, and they start spiraling inward, and eventually they merge together. At that moment, gravity waves start traveling outwards, and the last bit is such an enormous amount of energy being emitted that those waves, gravitational waves, can reach us 1 billion years after it happened. That's really spectacular. For that, they had to do measurements of distances because the shape of the space is being changed a little bit, and they had to build an interferometer to measure these distances, and then they found a signal on about, I think it's the 14th of August, a little more than 2 years ago, and they had two detectors, one in Livingston and the other one in Hanford, and they both found a signal. And that is a signal where suddenly they saw that the shape of space changes. It's a signal that oscillates because of the rotation of the black holes, but very fast. So the frequency is very high, but at the last moment it goes up even further. And it suddenly makes a high frequency burst with high intensity. It's called a chirp. And now I'll show you, actually I'll show you, but also let you hear it. So this is the signal where it goes, this is sort of how it builds. So you see the time goes this way and then suddenly it happens. So now if I go the next, it's called a chirp because the frequency goes up like a bird. I mean, I like the way that the New Yorker sort of made the cartoon the next day. It says, was that you I heard just now, or was it two black holes colliding? Of course, it was a joke if you only know that the signal's called the chirp. And so this is where you have to know some physics. So this was rewarded the Nobel Prize yesterday, and I'm actually going to show you about a quote that I read that Rainer Weiss gave one of the laureates on a telephone interview. Namely, this signal is very tiny. I mean, it's really a very tiny stretch. It's less than a millionth of the size of the nucleus of an atom. Quite incredible that they could measure this. And the reason is that it's very hard to change the shape of space. So space is very stiff, enormously stiff. And this has to do also with that this phenomena they looked at has this very short time scale where it goes very fast and very strong gravity with these black holes. So all these phenomena and tests of gravity, here I've summarized them a little bit, are described and they're testing the equations of Einstein. I've written down these equations here. You don't need to be able to understand what I write down, but this is what Einstein wrote down as his law of gravity. And it describes black holes, it describes the radiation from binary pulsars, bending of light, and things in the solar system. Many ways we've tested this. So why, again, do you need a new theory? And for that, I'm going to do a little experiment where I'm going to show that indeed there may be things that we don't understand if we think about it too simplistically. And I'm going to do an experiment. It's not with gravity, but it's with elasticity. Namely, elasticity is also about changing the shape of a material, and it has a certain way of describing what's going on by simply saying, if I apply a force, I know exactly how the material changes its shape. So I can even measure a force. So this is a material that bounces like a bouncing ball. It does it again. Of course, the bounce is very short, but I can measure also the mass, because if I put it down, then there's going to be a small dent in here. If I know the elastic properties, I can calculate from the size of the dent how heavy it is. So I'm going to test if there's some dark matter in here. Because I'm going to do a test where I put it down. And I'm going to wait what happens to that. If I apply the theory of this elasticity, nothing should happen because the force doesn't change. But something is going to happen, very slowly. So suddenly, you start seeing that the laws of physics depend on how you probe a system and on what time scale. I'm going to say that what happens in our dark universe is something that happens at a totally different time scale, and we're going to need a new theory, namely, that's not the theory of elasticity there. Well, the theory of elasticity, of course, is only a theory that we know works when we look at the whole object, because inside there are molecules. And I have to understand what really the stuff is made of to understand what the material is doing. So you have to go to the microscopics and derive the laws of elasticity. And I'm going to do the same thing with gravity. I'm going to go to think about what is space-time made of microscopically, and then depending on its properties, it can either give gravity like general relativity all the time, or it can do something else. And this material is going to do something else because it's actually going to flow. You can watch it, it's going to actually make a dent deeper and deeper because it's made out of a polymer that's changing its shape because these polymers are moving around, but they do it very slowly. This is still a putty, by the way. You can buy it. In the dollar store, actually, I do it once in a while. I go to the dollar store and I buy a couple of them, and so I did last week. There are actually tiny eggs that are a little bit in it, but I put some together to make a bigger ball. So if you want to do this experiment at home, just go to the Dollar Tree store and then you buy it, and it's fun stuff. So this is where I am going to go now to galaxies. So does gravity work the same at galaxy scale as general relativity would say? Well, some people say yes, of course, because Einstein is right. There's no way that he can be wrong, and therefore we apply Einstein's equations here, and we're going to learn things. But the other way you might say, well, let's test it, which is usually the way you should do things. Let's test it. There is a galaxy, we're going to see how they rotate, and we see what the velocities are as a function of the distance. Now here you see, you sort of make a model where you think that everything is going in a circle. We look at the color of the light, we know the redshifts, we can calculate the velocities, and then we see that the velocities start doing this. But then we look at the amount of matter, and most of the matter is in the center, and the same what we did with the solar system would have predicted that Newton's prediction would go like that. It doesn't work the same way. I've showed you gravity doesn't work the same way because I did the measurement. This is not what people say. People say, no, it works the same way. There must be more gravity here because it's going much too fast. And they made a fix. Not a tiny planet that explains the deviation of Mercury. No, an enormous amount of matter is going to be added there, and they call it dark matter. And they searched for it and searched for it, and they don't find it. Maybe there's another explanation.
Journey.
So here is, again, the same experiment. We look at the distance, we look at the way that the velocity goes, and we see a deviation. So this is Newtonian prediction. Actually, it's very much like the planets were doing, going down. And indeed, because most of the matter here is in the center, do you expect the velocity to go down? No, it stays constant. It really goes much faster, and it would not stay together if there would not be an additional attractive force. Of course, people say that's because there's more matter, but what is really happening here? Is there more mass that we are missing, or is there another explanation? So this is the dark matter hypothesis, is really that there's some collection of particles around our galaxy and other galaxies that explains this faster rotation. And this is called the dark matter halo. It's shown in blue. That's not the actual color because you cannot see it, but this is an artist's impression. But there might be another explanation, but this is sort of a representation of the fact that there's more gravity needed to keep a galaxy together. So I'm going to indeed say that this is something to do with the fact that gravity is emergent, and we have to understand what is made of more microscopically. There's other evidence that people point out. I mean, there's lensing again at much larger scale. This is lensing of galaxy clusters, where you see a cluster, a galaxy on the background being repeated many times. If you see these arcs, that's sort of the image. And you can calculate how much mass is then needed to explain this, and you find that a much more mass than we see in terms of these galaxies. So this is again seen as evidence for a stronger gravitational acceleration, and therefore people say if we apply Newton's law here as well, or general relativity, we should conclude there's dark matter. And this is then the picture that people develop, is that at larger scales in our cosmos there must be a web of dark matter, and this has to do with how the galaxies and all these things form. And indeed you can do these measurements using lensing. Again, this is called a weak lensing map, where you map out where is the gravity and where is the matter, and you see that there's even locations where there's gravity where there's hardly any matter. And this is used as evidence. Even further back, if we look at larger scales, what we do when we look from our planet out into the universe, light has to travel towards us and takes an amount of time to get towards us. That means that we look at objects further away, which are further in the past. So this is, you might say, an image of distances, circles that are bigger, but actually it's also times that are earlier in the past. And there's some furthest distance where we can see, where we see the light coming from what is believed to be the Big Bang, afterglow of the Big Bang. It's called the cosmic microwave background, and this is, after that we cannot look any further. So we have a largest distance we can look, and this is the way that people build a current cosmological model, and you can then estimate what is the amount of energy in our universe and the amount of matter. And the result is kind of shocking, that if we understand the matter that we are made of ourselves, like protons, neutrons, and everything in the planets and the stars, and we add it all up, it's much less than what is actually needed to explain this universe. So this is the budget for energy and mass together. Actually, I put energy and mass together because E equals mc squared. And then you see that 95% of the energy in the universe is not understood. It's sort of missing. The ordinary matter is this 5%. There's this cosmic microwave background that's also a lot of particles, actually. This is this bit. It's less than a percent level, 1/100th of a percent of all of the energy. So the energy in the photons is very little. But most of the matter is dark. That means we cannot see it. It cannot be the kind of particles we are made of. And this is the matter that people are looking for. And then there's dark energy, which also is not known really what that is, but it plays a role in explaining the expansion rate of the universe. So the universe expands accelerated way, and that can only be described by adding this additional energy to our space. Now, this is already telling me that something may be wrong, because we are deriving our laws of physics only based on this part, but what do we know about this? And Einstein describes this, by the way, by adding just a constant to his equation. And that adds sort of like 70% of the energy of the universe. I mean, that's a bit of a waste, but the other thing I already mentioned, this is observational reasons to go beyond the Einstein theory, in my opinion. But the other one is theoretical. I'm going to make now a case that the equations that Einstein wrote down can actually be indeed derived in a way similar to thermodynamics. And this is where this story of emergence, gravity, and the link with information are going to come from. And for that, I'm going to go back to the topic of black holes. Namely, black holes give us the hints of why there is a connection between gravity and information. So black hole is where all the matter is located in this very tiny part of space, so small that the matter collapses on itself and gravity becomes so strong that light cannot even escape. So black holes have a horizon, sort of an imaginary sphere around it, that if you would go beyond that, then there's no way to escape. So they have a size, and that depends on the mass that you put in. A larger black hole, a more massive one, is also bigger. By the way, the black holes that collided in these gravity waves are like 60 times the mass of the sun. So there's really a lot of mass in those. And they are big objects, like tenths of kilometers or maybe much more even. And actually there are in the center of galaxies even much larger ones. So black holes exist. That's a prediction of Einstein. But as theorists, we like to think about it as objects where we can learn a lot about gravity because they're the most extreme. And this horizon is going to play a very important role in understanding more about gravity. So let me give you a little bit of a feel what is going on. So I told you that if I take the shape of the space-time, when we have a mass sitting there, you can actually compare this to a sheet of rubber where we put some mass locally and we get some dent in it. Actually, here is some analogy with elasticity already happening. The mass is really creating the deformation of the space-time. But when the matter gets more concentrated, this gets deeper and deeper, and there's some limit where you just get a hole. That's where the black hole appears, and then there is some distance where light can no longer escape. So I want to show you a little bit what it looks like to be close to a black hole. Black holes also curve light, just like other objects did, and they bend light. So if Earth would be rotating around a black hole, it looks like this. You might get worried that Earth is being deformed here. That's not what's happening. This is the image of what it looks like, because Earth, when it comes back to the front, is just nicely round. But the image of Earth gets projected around with the light, where you again see the ring. But that was the Einstein ring that I talked about. It's just the light going around. Now I'm going to show you what it looks like if you fall into a black hole. It's an image I took from the internet. I should have acknowledged the person who did this, but I forgot. But anyway, this is a simulation. We're not going to do it for real. So it's done with the equations, and actually no one has fallen into a black hole, so I cannot really verify that this is true. We have had all of a kind of discussions, really what happens when we fall into a black hole, whether the horizon is really something you can fall through. We're going to see that we're going to be able to do it. So we're using Einstein's equations and then see what happens. So a number of things are going to happen. So there's a picture, and we're going to go around it, the black hole. There's a certain distance where you can simply make circles. You don't have to do anything. But when you get closer, there's some moment when you get drawn into the black hole, and you have to use an acceleration, it's like a rocket engine, to stay out. Then there's a distance when there's no stopping anymore, you falling in, and you eventually will cross the horizon, and when you cross the horizon, you continue, but you will go to the center and hit the singularity. But the horizon is a special location because light cannot be emitted from that anymore, and also because clocks start going differently. The time stops basically at the horizon. So we're going to see a clock here that's going to keep track, and that's going to go slowly. So I'm going to show you what's happening. So here we go. Actually, the picture, or maybe I should show this first, tell this first. Well, we're going to see it again. The picture actually was the galaxy, and it's been deformed as a lens. So we have here the horizon appearing. Strangely enough, the north and the south pole are a little bit off, and that's because, again, of the curvature, the bending of light. And we are there still in a safe regime, which is yellow, but now we have to start using the engine. And we set it closer and closer. Eventually, we're going to go through it. And then, indeed, you see that we have no connection anymore with the outside. And this is where there's no stopping us from falling on the singularity, and eventually time stops. I'm going to show this again because most people want that. So there we go again. So this indeed was a galaxy, and this is an Einstein ring because it's the way that the light gets around. And then we see the horizon appearing. And so this is where light actually is going around. And there's one particular distance which is called the photosphere, where light just makes circles. We see a flash when that happens, because that's not the horizon itself. The horizon is here, and this is where you need the north and the south pole. And they have not drawn what's inside, basically because it's unknown. So now we're inside, and we can only look outward. And we can still see a bit of the light coming in. Actually, light can still go into a black hole, but it cannot go out. So you can still see where you came from, but there's no way to communicate back to people outside. So it's fun to think about black holes, and this is also why the theorists do thought experiments near black holes. And two famous people, Stephen Hawking, well known here, of course, and Jacob Bekenstein. they both thought about black hole horizons, and they wanted to know more properties like the thermodynamic properties. If I throw in a box with gas particles in it, it has an entropy. This is where the connection with information is going to come from, because we want that the laws of thermodynamics are still true. Turns out that also the laws of quantum mechanics are going to play a role, and indeed what Bekenstein and Hawking showed is that if you throw in some matter in a box, some gas, the horizon gets bigger, but the entropy in the box disappears. But entropy always has to increase, and they made the assumption, that was actually Bekenstein, that the horizon area has to do something with the amount of information that you throw in, the entropy. Bekenstein did this calculation using quantum mechanics, and he found a very surprising result. Namely, black holes, nothing can escape. But it turns out, quantum mechanically, it emits radiation. And actually gets smaller. And the reason is that in quantum mechanics, you have the uncertainty principle, that there is a possibility of creating pairs of particles in the vacuum. And they are a particle and an antiparticle, where one drops in the black hole and the other one escapes. Normally, in empty space, they would reunite again and they just annihilate each other. But here, one drops in and the other one escapes, and you get radiation coming out. So this is the picture here. It's also where these two particles near the horizon, one escapes and one falls in. But if they are not on the horizon, then they can combine again. And this is going to be telling us something about the properties of this black hole, namely that it has a temperature, because its radiation is thermal radiation. And if we have a temperature and we have a mass and therefore an energy, we also have an entropy, and that entropy is a formula that Bekenstein already wrote down, namely that it's proportional to the area. So it has thermodynamic properties, precisely the quantities that I introduced as being emergent. The temperature and an entropy. And the entropy for a black hole is proportional to the area of its horizon. This was one of the more important discoveries. Actually, already 40 years ago, they made this. And I think it is the first crack in Einstein's theory. Nothing is perfect, and actually that's one of my storylines, is that every theory eventually gets replaced by a better one, and you have to look at the right clues of where to look, and you find that the black hole entropy formula tells you something about what is the microscopic origin of gravity. By the way, I already said that Newton's law had something to do with areas. This area of the black hole horizon is the same area actually we're going to talk about. So there is an entropy formula that tells us how much information is contained in a black hole. And we're going to think about this information as bits. I told you information for me is bits. It's also can be measured by entropy, because that tells us how many bits there are. And this is why this formula tells us how many bits we can associate with a black hole. Not ordinary bits, by the way. It's going to be quantum qubits a little later. So the information that is associated with black holes is not the information that we have classically on a computer. It's going to be the next computer. Actually, a black hole is the best computer you can have, because you can store an enormous amount of information on it. Namely, the density here is the Planck scale. Try building a chip like that. This is where the limit is. This is how much information you can store on a surface. And it's, as I said, not ordinary bits, it's quantum information. And now let me explain a little bit more about what that is. I already said that bits are zeros and ones. Quantum bits, they are also zeros and ones, but you can also think about it as the spin of an electron, for instance. The spin of an electron can be either up or down, but it can also be something in the middle. And we call that a superposition. So it has to decide still whether it's up or down before I do a measurement. And this is why a qubit has many more possibilities. So a bit has only two possibilities, 0 and 1. A qubit can be thought of as a sphere. All points on this sphere is a different state of a qubit. And this is why if you do calculation with qubits, you're doing many calculations at the same time. Many more bits than we normally have in a classical computer. In a quantum calculation, you do all these things parallel. All calculations are being done at the same time. This is why quantum computers are much more powerful. More importantly, these qubits can be entangled. I already mentioned what that is, namely that if I measure two qubits, that the outcome is the same. This was discovered, let me do the calculation, it's like 80 years ago by, again, a familiar name, Einstein, together with two colleagues. Actually, you may wonder why Einstein does something with quantum mechanics, because he didn't like it. Well, this was also motivated to show that there's something very funny about quantum mechanics, namely that if you measure an object and you measure the spin here, it can determine the outcome of a measurement somewhere else instantaneously. He called this spooky action at a distance, and he said, this cannot be. This paper was not that important at the time, but in recent times, it's one of the most important papers because it's the first paper where they explained entanglement very clearly. And this is what makes entangled qubits. It's the power of quantum mechanics. It's the essence of quantum mechanics that we have entanglement. And our universe is very entangled. And so this is why this is the kind of information we're talking about. So it's a property of the quantum bits. And actually, it's something that is already there before you start measuring it. It tells you that if you do a measurement here, that something else happens somewhere else. So this is already the qubits that I showed before. I mean, this is where indeed you have a 0 and a 0. If you do a measurement of this one, it can be either a 0 or a 1. So here, and the other one here, the other outcome might be a 1, but the outcome is always the same. So if I measure this one as a 0, then this one will be 0 as well. And if it's a 1, the other one is 1. But a priori, there's 50-50 probability when I do the measurement. So this is called entanglement. And I'm going to denote this by this picture of a sphere by connecting a little line between it. So entanglement is like a connection between two of those qubits. So I'm connecting qubits together, and this is the way I'm going to build space-time. So this is going to be my microscopic picture of the molecules of space-time. So this is what Bekenstein and Hawking calculated. They calculated that there was an entropy associated to horizons, and this has to do precisely with this pair creation, because here we are creating a pair of entangled particles, and they describe the amount of information. So the entangled qubits is really what's being counted by this formula. So this is the answer. So what is this entropy counting? It's entangled qubits. And they are the building blocks of space-time. And they are measured by the area. But I'm going to say it's the other way around. Actually, the amount of qubits is going to determine the geometry, and it's going to determine the area. So the geometry of Einstein is going to be derived from this language. So this is as far as I want to go, at least explaining the ideas. This is a current state-of-the-art kind of development going on in theoretical physics. Thinking about gravity in terms of quantum information and deriving its laws just the same way as we derive the laws of thermodynamics. And that's called emergent gravity. And this is where I want to connect now, final slides, to the dark universe. So here's a slide summary. Space-time and gravity are emergent. And this is actually a lesson we learn not from just black hole physics. I didn't tell you about string theory because I have only that many minutes to talk. But string theory itself also actually hints in the same direction. A lot of what we're learning nowadays comes from studies in string theory where we also see that this emergence of gravity from quantum information is very natural. This is all theoretical physics. And you might say, well, why are we doing it? Are we learning anything new? And in particular, is there an observational evidence? So one thing that I have to mention is that we have to rederive first the laws that we already know from this idea. This can be done. And I wrote a paper already about 7 years ago, a little more, which was called On the Origin of Gravity and the Laws of Newton, because that's one of the laws you want to derive. And what I showed here in this paper, that indeed if you assume that the amount of information, this entanglement, is proportional to the area, that's an assumption, by the way, then you can derive Newton's law. Just by using the same tricks that we use to derive thermodynamics. So there is Newton's law. And here's this picture of the information stored on a surface, and we find indeed the 1 over r squared law because the area, it grows like the area. This, by the way, as I said, is an assumption, and you may wonder whether this assumption is true. And this is where the possibilities are maybe to explain what's going on here. So now I'm going back to my original question. Is there some way that something strange or different happens in this galaxy? I already told you that the observations tell us that something different happens, but can we also explain this theoretically? Indeed, I'm going to say there are different laws acting here, because the laws that we have currently derived, Einstein's equations, are derived from observations that we have done in the previous century, colliding black holes, lots of stuff. But if you think about this question here, how long have we been observing the universe? If you think about the history of the Earth, actually this was from a slide actually from the internet. I could have put the universe here. The history of the universe, if you would take that to be 1 year, then humans only arrived 1 minute before midnight on the 31st of December. And how long have we been doing science? Fraction of a second. It's like taking a snapshot of the history of the universe and then drawing conclusion about its entire history. I showed you this experiment. The snapshot was the bounce. What happens to the universe is this, and there's a lot of dark matter in here because it's created an enormous dent. If I would apply my theory of elasticity to this, I would have drawn the wrong conclusions. So if the universe has this kind of slow dynamics happening at very large scales, we can explain these phenomena. And now let me go back to the picture here about what we don't know about the universe. This is what we have used. And let me ask you the question, according to current theory, where is all the information sitting? In this picture. Any idea? That little tiny yellow stuff. It's the photons in the CMB. That carries most of the information according to current theory. I think that's wrong. All of the information is contained there. Most of the information. And then we have a totally different way of thinking about it. We're missing most of the entropy. This number is 10 to the 90. That's the number of bits you would need to describe the photons. This number, I claim, is 10 to the 120, because that's the size of the horizon of our universe if we would have only dark energy. So this is going to be the conclusion. I'm going to think about our universe as if we are living inside a giant black hole, which has a horizon, except we are not outside the black hole, we're inside. Why do we can think about the universe as a black hole with a horizon? Is because of the following fact. We know, according to Hubble, that things move away from us with faster velocity when we go further distances. So objects further away move further with higher velocity. So this is Hubble's law. The velocity is proportional to the constant of Hubble, times the distance. So there is a distance when this would become the speed of light. And things that are moving faster than the speed of light we cannot see. So there's a furthest distance we can see, and therefore we have a horizon, which distance is given by, well, you take the velocity to be c, and you divide by h. So this is the distance to the horizon. If we would be in a universe which is constantly just expanding according to the Hubble law. This tells us then the size of the horizon, the size of the universe, and actually also the size of the number of bits I need. Namely, it's going to be the size of this horizon, again, measured in Planckian units. I'm going to claim this is information associated not to the horizon itself, but to the dark energy. There's an observational fact. Well, maybe I should tell you the picture first. So I'm going to explain what happens in galaxies' rotation curves. Namely, there's information contained in the dark energy. The matter actually pushes it away. It's like elasticity pushing it away. It creates a hole in it, but entropy wants to move back. It sort of wants to increase. It pushes back. I've done a calculation. If you don't believe me, I should take this aside because all the equations are on the blackboard. These are the equations of a paper I wrote about a year ago that does a calculation where at the end of it, I'm going to explain the data that are here. And let me already tell you a curious fact that should be been a smoking gun for why this is the right explanation. If you look at this curve here, so this is what Newton would have predicted, and this is what we observe. Turns out that the deviation always happens at a very particular gravitational acceleration, independent of the size of the galaxy. If you calculate or measure, I should say, that acceleration, turns out it's related to the Hubble parameter, which is very mysterious because a galaxy is a very tiny object, so what would that relation be? I explained that in that paper, and the formulas are like here. So I use entropy, the temperature, entanglement. Eventually, a formula comes out that describes this behavior and precisely the flattening of these rotation curves with this velocity acceleration in there. So these ideas are connected to observations, and I think this is proof that quantum entanglement is the origin of gravity. Then you may ask, what is it good for? I get that question a lot. I always show this one. One of the questions I think we're going to change. I do think that this is a new view of gravity, but also of the cosmos. And we are interested, always have been interested in the question, where did it all come from? That's a question that drives our curiosity, and it takes us from science to technology and back again. And it brought us from the period of the caveman to our current time. And it's therefore the driving force of what we are doing. Curiosity about nature, and then in the meantime developing technology as well. So this is, I think, also for me, my motivation. And maybe what we learn about understanding about quantum information and the universe will help us also apply it in some real things that is good for us. All right, thank you very much.
Terrific. That was all right. Let's open the floor to questions. That was terrific. So the microphone for the theater audience is right there. You can form a line. And the online audience, if my phone works, well, I'll get that updated too. But if I get to go first, I'm happy to go first. All right.
No questions? There must be.
There will be questions.
Okay.
So let's start with this one. So what first inspired you to become a physicist? And then the part B is, what prepared you to ideate something that goes so against the grain?
As a teenager, actually, I watched a documentary where Stephen Hawking was already in it explaining about black holes. And my future thesis advisor, Gerard het Hoofd, was in it too, explaining about elementary particles. It was in the mid-70s. The program was called The Key to the Universe. I was 14 years old and decided I wanted to do this. So this is what I started doing. And in particular, the question about black holes and entropy is something that Gerard Hoofd and Stephen Hawking discussed around for many decades, and I joined in. And I felt a number of things that the connection with thermodynamics already told me something about the emergence of gravity, but I have to admit, I always felt a certain unease with the way that people have extrapolating our current laws of gravity to describe the evolution of the universe and come with a very illogical thought, namely that there was a moment that suddenly, from nothing, it exploded. So I think that is a question that I want to eventually understand differently. And I think this idea of emergence sort of grasp, I find this philosophically much more appealing than the way that that's been done. So I feel there's something to be done, and I have been making progress on black hole physics, and other people have with string theory, that I feel that we are onto something. So I'm excited about that.
Thank you. Let's go to the theater right here.
Going against standard model of cosmology, you must come across all the objections. Do you address in any of your papers the objections like the power spectrum of the CMB and bullet clusters and all those other secondary evidence?
Yeah, so the bullet cluster I already addressed, actually gave a talk this afternoon where I explained some more of the details about this, but also what I explain here. So one thing that happens is if you think about how Einstein changed gravity from Newton, he didn't take Newton's law and write down a new force law. He had a totally different concept on where it came from. And so what people are doing now is excluding the possibility that we take Einstein's equation and write some other equation. The thing that really is changing is that's a totally new concept, and it has to do with the slow dynamics that's taking place. So there's no immediate connection between the location of the matter and whatever the gravitational field is. That can have a delay in it. And actually the collision, like the bullet cluster, can be explained in that way. And I also feel like the reason why people try to exclude these possibilities, I think is in part because they allow themselves only a limited class of possibilities. If you want to, so how should I say this? If you think already what kind of modification there could be to GR, many of them are probably not correct, but there might be one. And we have to think, I do think we have to think out of the box, because these problems are large ones, and we don't know yet where the answer is entirely. But I think to make a business out of excluding other people's idea, somehow I don't think that that's my way of doing things. I like to construct things, not destruct.
Peter.
If energy can't be destroyed, then what happens to the energy contained inside virtual particles when they disappear?
Ah, good question. So there's a certain moment, so there is uncertainty, and that means the following. If I look at a system very long, I know that energy, I can measure it. But if I look at it very short, I don't know really what the amount of energy is in there. And that's what Heisenberg taught us, that there's a certain uncertainty in how short you look at this object and what the amount of energy is in there. So for a short amount of time, space can borrow a little bit of energy as long as it gives it back a little later. And that's sort of the way that it happens. And it's like you cheat with energy conservation as long as others don't.
We'll go to an online question. So, would the discovery of dark matter invalidate your theory, or would some parts of it survive?
So that is also a good question. I mean, I don't say that there are no other particles to be discovered. The dark matter particle has to be a very special kind. Namely, it has a particle that does not decay, it has to stay around. And we have to explain why there is the amount that we observe. And many people say it may not be one particle, so they can add one or the other. So what I will say is that we can discover new particles, but it should not give us so much more matter in the form of particles that it starts changing the way that my equations work. Because then indeed these ideas are wrong. It's true that there are still many steps to be taken. So, but I can indeed quite confidently say that I really think there will be no particle found. And if it happens, I will have to go back to the drawing board.
Thank you. In theater.
This may demonstrate my ignorance, but if information, the amount of information is directly proportional to area, can we explain space-time in terms of 2D rather than 3D?
Also a very good question. I mean, certainly things that we have been working on is a model what we call holography. So a holography is indeed a projection of the three-dimensional space on a two-dimensional plane. And then you would say that all the information that is contained necessary to describe what's happening in that space can be recast in terms of two dimensions. So this is a theory that came also out of string theory. There's a space which has not positive dark energy, but negative cosmological constant called, instead of de Sitter, it's called anti-de Sitter. This is precisely a space where everything seems to live on the boundary, and we're trying to reconstruct what's going on inside for already 2 centuries, for 2 decades. And that is also taking a lot of difficulty. And I say that's not the space we live in, not the universe we live in. So what I did here actually was show that not all the information is actually really living on the boundary, but it's also filling up the volume. It still satisfies this area law that if you add it all up, gives you exactly the size of your horizon. So I think I would hate if the laws of physics would be eventually so that I have to construct what's happening in this room from some 2-dimensional surface, the boundary of our universe. That would be not a very practical way of doing things. And I have a feeling that this is also not going to be the final answer. Anyway, so it's a little bit of a subtle issue because we're still in the middle of this development. Maybe I could show you this next slide even, because there's a bit of this picture. This is the picture I mentioned, which is where there's a theory on the boundary that's describing something happening in the bulk, which has the volume, which has gravity inside. But this is then the hologram that we're talking about. And string theorists are doing this kind of stuff.
Ladies and gentlemen, Dr. Eric Verlinde. That was really good. Welcome to Perimeter Institute, and welcome to Perimeter Institute's public lecture series. For those of you that don't know, Perimeter is located in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone here this evening, both those of you here in the live studio audience and those of you watching online. The lecture itself will last approximately 1 hour and will be followed by a question and answer session. For those of you that are watching online, Dr. Kelly Foyle and a team of PI researchers are behind their keyboard, ready to engage in conversation and answer questions throughout the lecture. And if you want to ask a question, both during the lecture that way or ask a question to our guest speaker, use hashtag PI Live. And if you have a question for the guest speaker, get it in early so it has time to get all the way to my phone. All right, and now it's time to introduce tonight's very special guest speaker, Dr. Emily Levesque. Dr. Levesque is an assistant professor of astronomy at the University of Washington in Seattle. She received her bachelor's degree in physics from MIT and completed her PhD in astronomy at the University of Hawaii, and was both an Einstein and a Hubble postdoctoral fellow at the University of Colorado. Emily is a rising star in astronomy research. Her accolades include a 2017 Alfred P. Sloan Fellowship and a 2014 Ann Jump Cannon Research Prize from the American Astronomical Society. Dr. Levesque's research focus is on massive stellar astrophysics and the use of massive stars as cosmological tools. Tonight, she will discuss some of the strangest stellar phenomena in our universe and how these weird stars serve as a common thread for exploring our universe's history, evolution, and extremes. Ladies and gentlemen, please welcome Dr. Emily Levesque.
Well, hello and welcome to tonight's lecture. I'm extremely excited to be here and so happy to be sharing these very weird stars with all of you. I always like to start by putting up some pictures of some of the weirdest stars in the universe. So every object that you see on the screen right now represents some sort of bizarre or unexplained or particularly puzzling type of star, something that has surprised or confused at times astronomers. As I go through the talk and I look at things that are particularly weird or surprising, I'll be marking them with these little exclamation points. I can also promise you that by the time we get to the end of this talk, you'll be able to name every single thing on this screen. You'll be able to explain what it is, at least as well as astronomers can explain them, and you'll recognize all of them if you ever happen to come across them again. So to start off talking about weird stars, we need to establish what is considered normal for an object like a star. And to do that, I actually need to start with a diagram. So this is a very common diagram used in astronomy. It's called the Hertzsprung-Russell diagram. What we're doing here is plotting temperature on the x-axis, going from very hot on the left to very cold on the right, and plotting brightness on the y-axis, going from dim at the bottom to very bright at the top. What we can do with this is drop the collection of normal stars that we know about onto the diagram and see where they land. You can kind of see that there are clear spots where normal stars tend to hang out. I'll fill this in with a slightly more detailed version of the illustration, and you may recognize the names of some of the stars on the plot. I always like to point out where our sun is. So our sun is right in the thick of things, and our sun is really a kind of depressingly normal and unremarkable type of star. So the main thing that we use this diagram for in astronomy is explaining how stars evolve. And this is something a lot of people don't necessarily realize stars do. They're born, they age and evolve with time and change, and then eventually they die. And you can plot out how a star is going to live and die by following its path on the Hertzsprung-Russell diagram over the course of its life. You can see the sun, you can see that sort of diagonal of very normal-looking stars. The stars that I'm interested in, and the weird stars that we'll be focusing on tonight, are at the very top of this diagram. So these are the supergiants. These are massive stars. They're stars that are at least 8 times the mass of our sun or more. And I want to start by taking a short tour through these stars on the Hertzsprung-Russell diagram and looking at how they evolve. I like to use examples of stars that you can find in your own night sky. So to begin with, I want to look at Spica. Spica is a star in the constellation Virgo. It's an amazing example of a blue supergiant. So this is a massive star in the first phase of its life. It's fusing hydrogen into helium in its core. It's very hot. It's about 22,000 degrees Celsius. That's much hotter than our sun. Our sun is 5,500 degrees Celsius. It's about 7 times the mass of our sun, and it's about 10 times the mass of our sun and about 7 times the size. A star like Spica will stay in this part of the HR diagram for maybe 10 million years, fusing hydrogen into helium. Eventually, the star will run out of hydrogen, and it needs to try fusing something else. So it switches from fusing hydrogen to helium. When that happens, the stars actually go streaking across the top of this diagram from left to right very quickly. After 10 million years fusing hydrogen, they cross from the hot to the cool side of the plot in about 100,000 years. Along the way, though, they make a brief pit stop when we would consider them yellow supergiants. And we actually have an amazing example of a yellow supergiant that we all know really well. Our North Star, Polaris, is a yellow supergiant. This is actually pretty surprising because stars like this are rare since their lifetimes are so short. So it's pretty cool that our North Star is this relatively rare type of massive star. Once these stars have completed their trip across the diagram, they wind up as something like this. This is Betelgeuse. It's in the constellation Orion, a constellation that I'm sure many of you are familiar with. It's very easy to find in the night sky if you look for those 3 stars that make up his belt. And you can see Betelgeuse as his left shoulder. It's a very bright star that is very obviously red. Betelgeuse is an excellent example of a red supergiant, which are one of my research specialties and a particularly fascinating type of massive star. What's interesting about a star like Betelgeuse is that as it has cooled off and moved across the Hertzsprung-Russell diagram, it's also gotten enormously big. This star was born with maybe 15 or 20 times as much mass as the sun, but it's 900 times the sun's size. So I want to try and put that into context. This is the orbit of the Earth. That one dot in the center, it shows up as a couple pixels on the projector, is our sun. If we back up a little bit, we lose sight of the sun, but you can see the size of Earth's orbit relative to things like Jupiter's orbit and Saturn's orbit. If we were to put Betelgeuse where our sun is, it would stretch out to well past the orbit of Mars. It would begin approaching the size of Jupiter's orbit. So this is incredibly big and in its own right makes the star a bit weird. There's a couple funny consequences of a star being this big and this cool, and I want to again try and compare it to the sun. So this is an image of our sun, and if you were to zoom in on it very close, you would see things like this happening on the surface of the sun. These are called granules. What we're seeing are the very tips of a convective layer in the top, near the surface of the sun. What we're seeing is gas that starts out hot, rises to near the surface of the sun, cools off, and then falls back. It's not unlike watching bubbles boil in a pot of water. So on the scale of the sun, these are tiny, but stars like red supergiants do this too, and the effect is a good deal more dramatic. So if I put the sun away, it is now a single pixel on the screen, but I promise you it's still there. We can, to scale, compare the sun, there it is, to Betelgeuse. This is what those same little cells look like on the surface of Betelgeuse. The whole star is boiling and roiling and changing very dramatically when you look at how bright it is. This is a consequence of how large and how cold it is. And this is a normal red supergiant. This is very typical for stars like this. So it starts to establish why these stars are as interesting as they are. We went through the Hertzsprung-Russell diagram and we followed stars starting as hydrogen-fusing blue supergiants, crossing the diagram to briefly become yellow supergiants, and ending up as helium-fusing red supergiants. We can actually draw a line to represent the journey that we just followed. This is how a 15 times the mass of the sun star would move during the course of its lifetime on the Hertzsprung-Russell diagram. We call something like this an evolutionary track, and it's a great way to quickly and at a glance look at how a star is going to behave during its lifetime. This is actually a really great tool for studying theories of how stars evolve. This is an evolutionary track for a 15 solar mass star, but we can take a bunch of evolutionary tracks like that and draw them on a Hertzsprung-Russell diagram. We can look at what a 12 solar mass star will do, what a 20 solar mass, what a 40 solar mass star will do, and get a good sense of what normal massive star evolution looks like. So there's something you might notice on this diagram, and it has to do with how cold the stars get. Every one of these evolutionary tracks was computed using our understanding of stellar physics, and every single one seems to stop at about the same temperature. Everyone is not really getting any colder than about 3,000 degrees Celsius or so. To the right is this region where we don't think stars should be able to stably exist. Everything we know about stellar physics suggests that stars should not sit in this part of the diagram. Now, I mentioned red supergiants, and I mentioned that they're incredibly cold. We think that those stars should sit right at the edge of these evolutionary tracks, but for a long time, if we observed red supergiants, if we measured their temperature and we measured their brightness, and we tried to put them on this diagram, those stars would land here, in exactly the place that they don't belong. This bothered us for a very long time. We were trying to understand what was wrong with our stellar physics, what was wrong with our theory of how these stars evolved that could explain this really bad match between red supergiants and the predictions of evolutionary tracks. What finally clued us in was when we started looking at where the temperatures of those stars were coming from, and when we developed a very good way to measure those temperatures more accurately than we had before. The way that we'll do this is to take light from a red supergiant and sort it out into something called a spectrum. So in a spectrum, you observe light from an object, and you sort it out according to its wavelength. So the very bluest light will be on the left side of the diagram, and the very reddest light will be on the right. The brightness is still represented on the y-axis, so you can tell at a glance that this is sort of a spectrum of a reddish star because we're seeing more red light than blue. This is a cartoon version of what a red supergiant spectrum would look like. An actual red supergiant spectrum looks like this. It's a lot messier, and something you notice right away is that there are these strange sort of bites taken out of the spectrum. There's these little dips that show up periodically as we go from blue to red. All of those dips represent light that has been taken out of the spectrum on its way to us. That's light that's been absorbed by something in the atmosphere of the red supergiant. In this case, that is light being absorbed by titanium oxide molecules. These stars are so cold that molecules are able to form in their atmospheres. It makes the spectrum look interesting, and as it turns out, it's also a really good tool for measuring temperatures. If you look at a simulated spectrum of a red supergiant and you cool the star off, at 4,000 Kelvin, you really don't see that many titanium oxide absorption signs at all. As you cool the star off, they suddenly appear, and they get stronger very quickly. What it means is that we can use those dips in the spectrum as tools for measuring temperature. If we observe a star and we see very strong dips, that means the star is very cold. If we see very small ones, it means it's relatively warm. We decided to check this out as a means of maybe improving our temperatures for red supergiants and maybe fixing that problem that we'd come across on the Hertzsprung-Russell diagram. This was actually my very first research project. As an astronomy student, I worked on this after my sophomore year at MIT. I got to go to Kitt Peak National Observatory in southern Arizona. I had my very first observing run. You can't tell from this image, but I'm unbelievably excited because they're letting me open the dome of the 2.1 meter telescope, and I'm gazing up going, ha. We had 5 perfectly clear nights. This was wonderful observers beginners-like, and this has never happened to me again. And we got spectra of 75 red supergiants in the Milky Way. We used that technique, looking at those titanium oxide bites in the spectrum, to measure their temperatures, and then we replotted them on this same diagram. So when we remade this with our temperatures, the red supergiants moved from here to here. We had completely fixed the problem. This was enough, that little shift on the diagram was enough to get us unbelievably excited. Yes, we've done exactly what we set out to do. Physics isn't wrong. These stars work. This is excellent. Let's write the paper. And along the way, we wound up discovering something very cool, literally, and entirely by accident. So on this plot, we've depicted each star's temperature and each star's luminosity. And there's a very handy equation. This is the only equation that I use in the talk, but it's a very important one to have. There's an equation in astronomy that relates how luminous a star is and how cold or hot it is to how big it is. And I can walk through what everything in this equation means. L stands for the luminosity, how bright the star is. Well, we already knew that. We know how much 4 is. We know how much pi is, that's just a constant. And we know how much sigma is, that's another constant. We had measured temperatures, so now all that was left was the radius. We had everything at hand, so we figured, why not? This is just an algebra problem. If we move radius to the other side of the equation, take the square root of everything, we've measured radius. So we went ahead and calculated the size of every star in our list, and we put everything in a big table, and we started moving on to try and publish the paper. It took one of our research collaborators looking at this table and going, hang on. I don't know if you've noticed one of the numbers in this list, but it's astonishing. This is the largest radius I've ever seen measured. We might have discovered the largest stars in the universe. We went back and did everything again. We checked everything twice, but it turned out it was true. As part of this project, we had, by surprise, discovered the very largest stars that anyone had ever seen. So for comparison, I showed you where Betelgeuse sat if we put it where the sun was and compared it to the orbits of the planets. This is the size of our new record holder, a star named KY Cygni. It reaches out well past Jupiter. It starts approaching the size of Saturn's orbit. So this on its own, hitting this extreme of stellar evolution, most definitely marks KY Cygni as a weird type of star. So we've gone through how stars move on the Hertzsprung-Russell diagram. We've talked about these cold red supergiants fusing helium in their cores and how they can get fascinatingly big. But eventually, those stars also run out of things to fuse in their cores. Does anybody know what happens when we get to that point? Supernova.
You said it.
Yes. So to understand why a supernova happens, it helps to look at what's going on inside the star right before the supernova. Massive stars started out their lives fusing hydrogen into helium, then they moved on and fused helium into carbon, and they progressed fusing heavier and heavier elements. By the time they reached the ends of their lives, if you were to slice one of these stars in half, it would look like the inside of an onion, with layers of every single element that it's been using for fusion or as the product of fusion inside. This star gets into trouble when it starts to try and fuse iron. This fusion happening in the core of the star serves a very important purpose. It helps the star maintain this very delicate balancing act between the inward press of gravity and the outward press of that fusion. As long as that balance is maintained, the star is going to be alive and it's going to be just fine. Fusing iron disrupts this process because fusing something like hydrogen or helium or carbon produces energy. If you try to fuse iron, you need energy. So at this point, that delicate balancing act has been disrupted. And I have an animation of what happens once we do that. So in this animation, we're zooming into the center of a red supergiant, and you'll see the colors in the center of the star change to represent different fusion processes that are occurring. As we switch from fusing hydrogen to fusing helium, as we switch from fusing helium to fusing something like carbon, you'll see the color change again. And the star will progress through different fusion sources until it attempts to fuse iron. This goes terribly for it. And then in less than a second, that iron core implodes. All of the material in the outer layers of the star tumbles down onto that imploded core and then bounces back out. And that rebound bounce gives us this unbelievable explosion that we see as a core collapse supernova. So this is an incredibly dramatic death for a star, and supernovae are amazingly bright. This picture here is from a cave dwelling in Chaco Canyon, New Mexico. It shows a few illustrations on the rock. You can see what looks to be a daytime moon. You can see a person's hand. And then you see this. This, we believe, is a depiction of supernova 1054. This supernova went off on July 4th, 1054, and was in our own galaxy. It was very nearby. It was so bright that you could see it during the daytime sky for 2 weeks. We have historical records of it from Arabic astronomers, from Chinese astronomers. They called it a guest star because it appeared, stayed for a little while, and then left. This actually left behind what we now know as the Crab Nebula. The Crab Nebula is the remnant of that 1054 supernova, all of that material that got blasted off of the star now dissipating into interstellar space and giving us what we call a supernova remnant. That was an unbelievably dramatic supernova, and it was extremely bright, in part because it was so nearby. It was in our own Milky Way. We had a supernova like this in 1054. There was a supernova in 1572, one in 1604, and we haven't had one since. Every modern supernova that we've studied has been in another galaxy, and it's a little bit less of a fireworks show. So this is an image of M51. This is the Whirlpool galaxy, and it's an image from January of 2005. In July of 2005, a supernova went off in M51, and there's actually a really great image of that supernova happening. Did you see it? Such a dramatic explosion. Let me do it again. Yep. Usually when I turn it off, then I hear this, oh. So that was the dramatic supernova, 2005 CS. We name supernovae based on the year that they happen and how many we've seen in that year. So this supernova happened in 2005. We started with supernova A, B, C, D, and went through the lettering. So these supernovae are fairly common. You can tell if we got all the way down to CS, there's quite a lot of them. This was a pretty bright and still pretty dramatic by astronomy standards supernova. We cataloged it, and we watched it do what a normal supernova does. It got incredibly bright, and then over the course of about a year, it faded away. This is what an exploding star should do. Sometimes we see something a little bit different. So this is the beautiful galaxy, NGC 7649, and by galaxy I mean the little fuzzball in the middle of the picture. As we get farther away, the photos get a little bit less dramatic. This galaxy hosted a supernova, we thought, in 2009. This little bright thing appeared, we identified it, and immediately said, hey, we found another supernova. This is supernova 2009 IP. It got that name. We saw this thing get very bright. We watched it fade away, and we thought, well, perfect, another supernova doing its supernova thing. Journey. And then it reappeared in 2010. It reappeared again in 2011. In 2012, we finally saw a very dramatic eruption from this star, and we think that this star might now be dead, although people are still keeping an eye on it and looking here just in case. This was an example of a star that, from our perspective, was just pretending to explode. What supernova 2009 IP actually is an example of something called a luminous blue variable. We tend to name things really literally. In astronomy, we talk about, red supergiants, or our telescopes are named fabulous things like the Very Large Telescope. So, luminous blue variable is very literally what these stars are. They're luminous, they're incredibly bright. They're blue, which means a lot of the time they're very hot. And the key thing is that they are variable, so they change with time. A star like the one that produced supernova 2009 IP is variable because it's flinging off enormous amounts of mass that appear to us as something very akin to a stellar explosion. What we're seeing instead is an eruption, and we still have a very limited understanding of what causes eruptions like that. We have an amazing example of this in our own Milky Way. This is a photo of Eta Carina. It's about 7,500 light years away. And if you look at that image, it looks like you're looking at something that exploded. It looks like the violent post-death of a star. What we're instead seeing is material that got flung off of the star during an eruption in 1843. When that eruption happened, Eta Carina got so bright that it was actually the second brightest star in the night sky for a few days. It's faded away since then, but incredibly, the star is still in there. The star survived this explosion, and what we're left with is this very fascinating material from that eruption that we're still studying in the hopes of maybe trying to explain what luminous blue variables are up to. So I want to go back to the Crab Nebula, to this remnant of a supernova. I explained how a supernova happens. You have that collapsing core, material tumbling down after it, and then rebounding and giving us this explosion. The exploded material winds up giving us something like a supernova remnant, like the Crab Nebula, but there's actually something else in here that's worth highlighting. At the heart of the Crab Nebula is something called a neutron star. So a neutron star is what is left over when the core of a massive star collapses. Neutron stars are absolutely fascinating. They aren't working like the normal stars that I've described, these stars that have to fuse something in their cores to maintain a balancing act with gravity. These stars are actually supported by principles of quantum physics. They're supported by something called neutron degeneracy pressure, hence why they're called neutron stars. And the basic principle behind this is that neutrons that are very similar to one another, they have similar quantum properties, they occupy a similar state, cannot be squeezed too close together. They will literally resist this to the extent that they're able to support themselves against gravitational collapse. Neutron stars are unbelievably dense and unbelievably small. One of these stars is the size of the city of Waterloo. But if you took just 1 teaspoon of it, it would weigh more than a mountain. We're talking about a very extreme scenario in terms of the matter in this star. You also sometimes see something interesting from a neutron star. This is an artist's rendition, and you'll notice those lines sort of poking out of the star in opposite directions. Those are showing the magnetic field lines of the star and illustrating that some neutron stars can be what we call a pulsar. In some cases, these stars will emit light out of their magnetic poles. Now, we know on Earth that our geographical pole, the actual pole that the Earth rotates around, is different than our magnetic poles. In an extreme case like our neutron star, what you'll get is a beam of light pointing around as the star rotates and sort of causing a flash as it goes by. The best analogy that I've been able to find is looking at something like an emergency light on top of a fire truck or a police car. Those are two beams of light pointing out in opposite directions, and as you spin it, it appears as though something is flashing. That flash is what we detect when we see something like this, a pulsar. Pulsars were actually discovered in a pretty interesting manner. They were detected by a woman named Jocelyn Bell Burnell in the 1960s in the radio. She actually detected first 1 and then 2 and eventually got up to 4 objects like this. Their pulsations were perfect. It sounded like you were almost hearing a heartbeat from these stars. They temporarily nicknamed the objects LGM 1, 2, 3, and 4. And LGM was an abbreviation for Little Green Men. And they were mostly kidding. But it was a sort of tongue-in-cheek nod to the fact that this was such a perfect and regular signal that maybe somewhere Little Green Men were making this. It turned out that wasn't the case at all, and instead it could be explained by a neutron star that was specifically emitting this light and detectable as a pulsar. So I've talked about these neutron stars that can form when the core of a massive star collapses. If that collapse goes one step further, if we have more mass in the core, or if that neutron star gains mass with time, we instead produce something else. We produce a black hole. I apologize for the artist's omission. You understand. These stars will produce black holes as part of their deaths. Now, the black holes themselves are utterly fascinating. But what I'm particularly interested in are a subset of stars that actually do something very strange when they die and produce black holes. These stars produce something that we know as gamma ray bursts, and I have an animation of what this looks like. This is a massive star, something like 40 or 50 times the mass of our sun. Now you'll notice it's blue, it's not red. The outer layers of this star have actually been ripped off over the course of its life, exposing some of the hot inner layers. When this star dies, its core collapses into a very rapidly rotating black hole. That black hole starts consuming the star and almost shattering the star from the inside out. And it ignites these unbelievably high energy jets of material, shooting out perpendicular to how that black hole is rotating. It consumes the star, collisions in those beams, produce the gamma rays that we detect here on Earth, and eventually the death of the star ends with the same sort of supernova that we talked about before. So that whole video took about 15 or 20 seconds. That was in real time. A 40 solar mass star will actually die and produce a gamma ray burst in a comparable amount of time. So this is an incredibly violent death for a star. It's incredibly weird, and that's an amazing timescale to work on for something that huge. Those flashes of gamma rays that we see from stars like this were actually discovered by accident. So these are the Vela satellites. It's a sketch of these satellites that were launched in the mid-1960s following the signing of the Nuclear Test Ban Treaty. So the job of the satellites was to orbit the Earth, monitor the planet, and look for signs that somebody was violating the treaty and performing a nuclear test, which would have shown up as a flash of gamma rays. And the satellites worked great, and they detected many flashes of gamma rays. And fortunately for world peace, none of them were coming from Earth. Instead, they were coming from all over the sky. It took us a long time to try and explain what we were actually seeing when we saw these gamma rays. What we finally determined was that we were seeing flashes of these dying stars from other galaxies. We've now put up dedicated telescopes whose job it is to look for gamma ray bursts and to tell us when one has happened as quickly as possible so we can try and study them. So this is the SWIFT spacecraft. It's a tailored telescope for detecting these sorts of gamma ray flashes. That flat panel that you see on the front is a gamma ray detector. And then under what looks like a baseball cap, but is actually a sun shield, are X-ray and ultraviolet and optical telescopes that try to observe these objects as fast as possible. What SWIFT will do is it will sit there orbiting the Earth, waiting for a gamma ray burst to go off somewhere in its field of vision. It'll spot a gamma ray burst out the corner of its eye, go, oh my God, turn, and start taking data on the gamma ray burst as quickly as possible. When it does that, it sends a notification down to Earth to astronomers saying a gamma ray burst has just happened. Remember, that flash of gamma rays lasts 20 seconds. We see light from these events in other wavelengths, but they still don't last very long. So there's a great reason to try and go after these events and study them as quickly as possible. So this gets into a type of astronomy called time domain astronomy. I love this discipline. It focuses on trying to study things that are very fleeting and very quick. It's the closest, I think, that we get to sort of movie-style astronomy. So I want to do a quick comparison between how a movie might depict time domain astronomy, detecting a gamma ray burst and having to chase it very quickly, versus how it actually happens. I would contend that I think the way that we actually study these could be more interesting than a Hollywood film. But in Hollywood, if you detected a gamma ray burst and you wanted to do something very quickly with it, the detection would be announced by the science siren going off. For some reason, this is always a very public and very easy thing to do. Astronomers would get this notification that something exciting had happened. They would run to their telescopes, wearing lab coats for inexplicable reasons. They would look through the telescopes with their eyes, and they would naturally see something like this. They would see perfect, beautiful, colorful data. They would realize that something that they had observed would help them to save the world. They would dash off to talk to aliens or stop an asteroid or find a new home to live on. And that tends to be how the movie goes. The reality is a little bit different, but I think some of the things that we do are more fun. So in reality, a science siren does not go off when a gamma ray burst is detected. Instead, you get a notification on your phone. You will see a text alert or an email. There are astronomers who are signed up specifically to get notifications if something this exciting happens. Once that happens, the astronomer holding the phone gets to go, all right, we have now triggered something called a target of opportunity. There's something that's happened in the sky that we want to follow up as quickly as possible with the best telescopes possible. They will have access to something like the Keck 10-meter telescopes, which are on the summit of Mauna Kea in Hawaii. They will contact these telescopes and say, you have to stop whatever you're doing. I'm sorry, astronomer who is doing their own science. You have to stop whatever you're doing and take a little bit of time to observe this object in the sky very quickly before our chance goes away. I think that these telescopes are unarguably cooler than the lab coat and eye version that you might see in a cartoon or a movie. To give you a scale of what a 10-meter telescope looks like, that's a about 6-foot-tall person standing in front of one of the two Keck telescope domes. So you'll call in, you'll trigger this observation, and you hope that the night looks like this. You hope that it's beautiful and clear, and you can get amazing data of whatever you're wanting to observe. The night might look like this. This is an actual photo that I took when I was trying to observe at Keck, and when you can't see the building that's like 30 feet away, your odds of detecting something in deep space are getting really bad. You can't even open a telescope when it's this crummy out. It's unsafe for the telescope and the instruments. Hopefully the weather is clear, you take observations, and you get gorgeous data. This is beautiful data, and by the way, that's the thing you're looking at. The bright object up top is something else in the way. There's a lot that has to be done to data before it can be finalized. You have to account for things like the background glow of the sky, electronic noise from the instruments on